Let's just take a quick look at some basic principles of joint and marginal probability as we go through. You're typically going to see your data presented in this kind of problem in two different ways. One is you might be given a joint probability table. This is an example of a joint probability table where for two variables x and y, in this case this might be insurance deductibles on two different types of policies, you're given the probability that the pair of numbers will occur together. So in this case, it's a 30% chance that if x is 100, y is going to be 500. You know you've got a complete probability matrix because if you look at the entire 9-cell range, they do in fact add up to 1 over time. Another alternative, sometimes you're given a marginal probability, which is the probability of that variable independent of the others. So for instance, the probability in this case of having y equal to 500 is 55%, regardless of the value of x as it goes through. So that's its marginal probability. Likewise, the probability of having x equals 500 is 40%, regardless of the value of y as it goes through. So you're usually presented with one or the other of these. You're not usually presented with both, but from either you can get back to the other. So let's just take a look at the marginal probabilities from given our joint probability matrix. It's very easy to calculate. Just take the sum of the incremental cellular probabilities and add them up, and you get the marginal probability going through. So just carry that probability over, and if you look at their sum, you'll see that they do in fact add to 1. Likewise, for the marginal probabilities of x, we'll take the sum of the values associated with the row, and we'll do that twice, and we'll see that they in fact add up to 1. So those are, you end up with the marginal probabilities that you might have been given originally. So let's assume over here that we might have been given the marginal probabilities, and we want to work backward and figure out what the joint probabilities are. So basically the probability of it being 100 on x and 500 on y is the product of those two probabilities. So I'm going to take the m, I'm going to lock in the n column since I know I want to copy the cell, and I'm going to multiply that by the 55% at the bottom, again locking in using F4. I'm going to lock in row 6. I do that so that I can easily copy the cells as I go through. Okay, I lose my line on the bottom when I do that, but that's okay. I can put that back on easily enough. Okay, so now I have the joint probabilities derived from the marginal probabilities. And note they are not equal. What I've done down here on the lower rows, I've calculated the difference between the joint probability I was given originally, from which I derived the marginal probabilities, versus the derived joint probability that I got back by working backwards from the marginal probabilities. Now, if x and y had been independent variables, the final joint probabilities would have been exactly the same as they started out in the first matrix. The fact that they are different tells you that the two variables are not independent of each other. There is a dependence. So if you go through this process from joint to marginal, marginal back to joint, and don't get the same answers, then you know there's not independence. There's a dependency between the two variables. You don't necessarily know what that dependency is, but you know there is a dependency. So for instance here, the positive number means it's higher. So the original probability I was given was a 30% probability of the x being 100 and y being 500. But when I recalculated it, I saw if they had been independent, I only would have expected there to be a 19% chance that I would have had x equals 100 and y 500. So the actual joint probability that I was given is 11% higher than I ended up calculating. So that's more likely than one would be considered if it were considered equal. And in fact, I tend to have more down the diagonal, which basically says that independent of the statistics, if one person buys an insurance policy with a higher deductible of one type, they're likely to buy a higher deductible of the other type. And in fact, that's more pronounced. If someone takes the lowest deductible on y, they're much more likely to take the lowest deductible on x. The minus probabilities you'll see are at the midpoints and extremes. If someone takes the middle deduction on y, they're 7% less likely to take the lowest on x. If they take the lowest on y, they're even less likely to take that low. So there's a slight bias toward the numbers either being low together or high together. That's not a statistical statement. It's just my observation looking at the data, knowing where the data started on insurance deductibility. So statistics doesn't tell us what the dependence is. It only tells us that there is one. These two data variables are not independent.